talk about something quite specific, the conformal cube sphere. So if you are not interested in the conformal cube sphere and want to do something else, you are free to go. So anyway, okay. So that's something, well, you know, it's something I've been doing in the past 2 weeks, basically, and talked a bit with John McGregor and Alistair about, and something fairly simple, but which apparently hasn't been noted before if you used cube sphere grid. So that may be of interest. Certainly, you have to be aware of this stuff if you want to use the cube sphere grid to solve problems which involve the Laplacian operator, like typically Helmholtz problem, for example. Okay. Okay, so cube sphere. Essentially, there are two types: the conformal one, which is the one I'm going to talk about, and the gnomonic grid. So the conformal was introduced by Rancic et al. In '96, and the gnomonic is much older and was introduced by Sedon in '68, I believe. So the properties of these two grids, they have both have advantages and drawbacks. The conformal one is nice because it's quasi-orthogonal. It's also isotropic because it's conformal, and it's continuous. So there is no discontinuity at patch edges, which is an important thing. The gnomonic grid is nice because it's uniform in resolution. It's also simple, so the formula for computing the metrics are quite simple. The formulas for computing the metrics of the conformal grids are not that difficult, just a Taylor series expansion, so it's slightly more complicated, not very complicated. The conformal grid has a problem with non-orthogonal poles, and that has an effect on the Laplacian, which is what I'm going to talk about. And also you can see that there is convergence of the grid lines at the poles, which is, you know, something, arguably it's the main factor that people mention when they say, I don't like the conformal cube sphere because it doesn't have this uniform scaling of resolution when you increase the resolution. In the context of what I'm doing, it's probably less of an issue. But of course, that's linked to the non-orthogonality of the poles. These two points are linked together. The gnomonic grid has some problems too. One problem is that it's non-orthogonal. Okay, so if you want to discretize things on a non-orthogonal grid, you have to add additional metric terms, a bit more complicated. And also, which is probably more serious, it has edge discontinuity. So the coordinate line don't match up at the edge. And that's what caused, I think, suddenly to just forget about it, because he initially tried to use it and had problems with convergence at the grid edge. There are ways of getting around that, but it makes things a bit more complicated. So why am I interested in this? Well, what I want to do is combine quad-tree adaptivity and do quad-tree on the sphere, essentially. So one choice is to do the quad-tree and the conformal cube sphere combination. Just show you an example to give the context. So that's a Hale-Turiez spin-up simulation. So on the left side, you have the projection of the cube sphere. Okay, that's the 6 patches on the plane, so that's in computational space. Okay, what you see is the field of surface potential temperature. So the equator runs along the here, and that's the two poles. That's the North Pole and the South Pole. And what you see on the right is the adaptive mesh. So in this case, the resolution varies from 0.7 to 5.6 degrees. And what I use is an error indicator on the potential temperature field to adjust the field. So what you see that indeed it tracks the small scale features near in the storm track, basically. So maybe I can show you what it looks like. I have a nice movie of this. Plays. Okay, oops. Okay. Okay, so that's the initial spin-up. We start from an atmosphere which is at rest, and the Hale-Turiez forcing is just simple relaxation to other base states. So that's what it looks like. You can do statistics. The statistics looks quite good, and you see, of course, well, on this animation you can't see the resolution, which is good. But you can see indeed that you have very little features in the tropics because there is no moist convection in the Hale-Turiez test case. So the flow there is very simple, and of course most of the action is in the storm tracks at the mid latitudes. And that's something which is so captured by the adaptive mesh. And the adaptive mesh looks like that. So you see that initially it's convectively unstable, so you have the adaptive mesh actually tracking the unstable convection, and then eventually it reaches the steady state regime where the adaptive mesh tracks the storm systems in the mid-latitude. Okay, anyway, that's the overall context. I will talk about this at the Metaphysics meeting a bit more. So let's go back to the cube sphere. Okay, so just to remind you on general curvilinear coordinate notations. So what we consider as a mapping from R2 to R3, and it's x, y, z is function of u, v, the two coordinates in computational space. You have a metric tensor, which you can express like this. Here I introduced the scale factor, hu and hv. Okay, if you have for orthogonal coordinates, you have the cross term, the transverse term as 0. Okay, so you have a diagonal matrix. And for conformal coordinates, in addition, the scale factor are identical. So the Laplace-Beltrami operator is just a generalization of the Laplacian on a curved manifold. Okay, so in orthogonal coordinates, you can express it like that. So you have just a scaling which is linked to the area of the element, if you want, and you have here the ratio of the scale factors in the derivative. And it also verifies for any differentiable manifold, and of course on non-orthogonal coordinate also, this relation, so that the Laplacian or the Laplace-Beltrami operator of the coordinate vector is -2 times the average curvature, local average curvature, times the normal. Okay. So for example, on the sphere, you have that Laplacian of y is equals -2 over r over y, or x or y or z. That's the test problem I'm going to consider in this case. Okay, I'm going to verify whether this relation is verified for a discrete version of the operator. So I will consider the 3-coordinate system just to check that things work as you expect them to. So spherical, stereographic, and conformal cube sphere. The mapping is from -1 plus 1, and the radius of the sphere is 1. So the stereographic and conformal cube are both conformal mappings, okay, for which the scale factors are identical. So you can write the Laplace operator in various ways, and of course, one simple way is just the classical 5-point finite difference, okay? So you can write it like that. You just have the scale factor, the area, if you want in this case, and you have here the ratio of the scale factors, okay, evaluated at the right location on the discretization. There are various ways you can do that, but what I show is, is independent on the detail of the discretization. So test case is the simple evaluation. So that's the formula I had before. Okay, it's 2y, and here I consider the evolution on the mesh along the diagonal of the coordinate system. So if you look at your computational space, I'm just moving along the diagonal. Okay, and when u is equal to 1, you are in the corner, so near the pole of, for example, of the cube sphere patch, or near the pole of the spherical coordinate, if you want. And what I plot here is the error as a function of the number of grid points, okay, at various locations on the diagonal. So point 2 is close to the center of the patch, okay, and 0.99, which is this yellow curve here, okay, is close to the pole. And the red curve is just the -2 slope. So for spherical coordinates, that's what you get. So you see that irrespective of where you are on the patch, you get second-order convergence, as you expect, okay. And what you also see is that the error you make for this test case is pretty much irrespective, it's the same irrespective of where you are on the patch, okay? So you get local and global convergence. If you do that for stereographic coordinates, it's pretty much the same story. The error distribution is a bit different, but still you get second-order convergence and everything is fine. Now if you do that on the cube sphere, that's what you get. So here you are at the center of the cube sphere patch, okay? And then as you get closer and closer to the pole, actually the closest point is up there, the yellow curve. You see that you always get local second-order convergence, as you expect, but you see that the error, the absolute error, actually diverges as you get to the pole. You can actually quantify that. So I take a model of the error, just that. So it's a function of u times delta squared, okay? Because we saw you at second-order convergence. And what I did there, I did the same, but I fitted the prefactor. Okay? So that's the same thing here. So here we are close to the center of the patch, and here we are getting closer to the pole. Okay? And that's the evolution, the measured evolution of the prefactor. Okay? And you see, well, that the prefactor diverges with this slope, 3.23. Okay? And of course, for the spherical, you can do the same for the spherical and spherographic, and A of u is pretty much a constant. Okay? So in summary, if for this particular test case, okay, simple test case, on the conformal cubes here, we can approximate the error by this prefactor times 1 of minus u, which is the distance to the pole, minus 3.23 delta squared. Okay? So it means that now if you look at the uniform grid on your patch, the closest point to the pole will be at 1 minus delta, so you just replace that by u here. What you get is that the error, maximum error on your patch, diverges like delta to minus 1.23. Okay? So what you have is that you have local second order convergence, but you have global fast minus 1.23 divergence of your Laplacian operator. Okay? So why is that? Well, it's fairly simple really. If you look at the formula for the Laplace-Beltrami operator for conformal matrix, okay, the R factor is 1. So what you have is just the scaled by the surface area, the scaled version of the standard Laplacian, okay? But of course expressed in coordinate space, u and v, okay? Now if you look what happened for the conformal cube sphere, what you have here, what I plot here is the two components of the Laplacian, okay? d2y du squared, and then minus d2y dv squared, okay? So what you see is that as you get close to the pole, both of these components diverge. Okay, so the curvature along the coordinate line of the coordinate becomes infinite as you get close to the pole. But of course, there is a minus sign there, so these two cancel out. Okay, they diverge at the same rate, and of course, the value of the sum of the two is bounded. Okay, you still get exactly in the exact case. That's the green curve, which is the exact Laplacian. Okay, but now what you do when you do finite differences is that you difference this one using second order finite difference, and this one using second order finite difference also. And the errors accumulate.
Your picture of the grid, of the conformal grid, implied or seemed to suggest that you do not have a kink.
I will show you why you have a kink. It's fairly obvious. It's linked to the fact that the pole is non-orthogonal.
So it's the poles that are the problem, though, not the
It's
equator.
The pole. It's the pole.
Yeah,
Yes,
so
but that's
apparently-
the important
But
thing is
that's
that
directly linked to the non-orthogonality.
that's right. The important thing is that the influence of the pole is not local; it's non-local. That's exactly
Right.
what you see here. Okay. So because you have to match up, the coordinate lines become. You know that they become infinite at the pole, but they're actually finitely curved, but large curvature, slightly away from the pole, not very far. You know, not well, quite far from the pole. 0.01. Okay. So already at 0.01, so 100 grid points in the patch, you have curvature of the streamline, which are of several orders of magnitude higher than the center of the patch. When you discretize that using finite difference, your error goes up.
Yeah, but you can't just.
So you can trace back that I did with the full Taylor series expansion, but you can push the analysis a bit further. So how do you make this conformal map? It's a composition of two maps. You have the first map, which is conformal, which is in R2 space. Okay. And if you look at the Taylor series decomposition, of course, near the pole, you can just look at the leading order term. Okay, and it's z to the 4/3. Okay. What I've plotted, and then you have a second one, which is stereographic. We know stereographic is no problem. Okay, there is no problem with stereographic. So the cause of the divergence of the straight lines comes from the first mapping. What I have here is this first map. Okay, the z to the 4/3 first map, not the full conformal map, just the z to the 4/3. And what you see is this. So it's very simple. What happens is that you have all the coordinates line needs to be orthogonal, and of course at the pole, what you have here, this angle is 120 degrees. Okay, because that's what you want to get at the pole in the end, so that all the patch match up. So what you have is that you have a line here which is 120 degrees, and here it has to match up arbitrarily close to the pole to 90 degrees. So of course the curvature of the coordinate line is going to has to diverge. Okay. And of course, this exponent here gives you can work out, I didn't show that, but you can work out and it gives you directly what you observe in the numerics. That if you remember, it was 1.23, so it's actually, a fraction of 1/3, or factor of 1/3. Okay, so that was for the direct discretization of Laplacian. What about the inverse problem? So remember, that's important when you want to solve Laplacian, Laplace or Poisson or Helmholtz equation on the sphere. And then that's what really you want to solve. So the inverse problem is this, okay? And of course, the solution is phi equal y. So I do exactly the same thing now. I use the same operator, but I solve the inverse problem with the same discretization of the operator, and that's what you get. Which is not so bad at all. In this case, the error, so it's the L1, L2, and max norm. See that we get second order convergence for the L1 and L2 norm, and we get actually better than first order convergence also for the L max norm. So it's not perfect, but you can push that. So it's L8 levels, it's 256 squared. Okay, so we're already pretty close to the pole if you remember the curve before. So clearly the Poisson problem is much better behaved than the direct operation, which is not very surprising. You can think of it as an optimization of your mesh. I mean, you could use, once you have solved that, you could use the approximate solution as a coordinate function, okay? And if you inverted that, you wouldn't have any divergence of the Laplacian by definition. So you could see that as an optimization operation for how you construct a mesh, okay? That would be one way of fixing the mesh would be to iterate solve like that, for example. Okay, so conclusion. So the error of the discrete 5-point Laplacian operator on the conformal cube sphere diverges globally. Okay, so here you have to be concerned about this. The inverse Poisson problem, and also I didn't show the analysis, but lower order operators. Okay, if you look at gradients, they are better behaved. And of course, the divergence of the curvature of the coordinate lines, which causes the problem. That's the signature of the 120 90-degree polar singularity. Okay, and the big point there is that it's not confined to the pole. Okay, it converges fast enough toward the pole that the curvature is large enough, even finite distance from the pole, that it affects the whole bed. So the question is, can this be fixed? You really need to be fixed. So the simulation I showed of the L-sphere circulation was done using this operator. No, I didn't fix anything. So you could say, okay, maybe it works in practice, but it's a bit concerning that it's so badly behaved on idealist taste. So talking with people who use this grid, they haven't noticed problems, but one of the guesses is that they haven't pushed the resolution high enough that the problem starts to manifest itself. And I think it's going to appear eventually in the Poisson problem also if you push the resolution. So, and then yeah, Jean?
Yes. You're using simple finite difference. How about finite element? In principle, if you use test function, we would fill the singularities and could remove it because it's an apparent singularity. The physical.
Yeah, that's right. You shouldn't expect to observe this in a finite element scheme.
But even a finite volume.
I'm not sure. I mean, yeah, I mean that's a good point, but that would still be an. I mean, you could use that as an approach to, in effect, the finite element scheme, where you could reduce to a global implicit problem. So you will get regularization a bit like what you get when you solve the Poisson problem, the inverse problem. So yes, in this sense, it could probably fix it.
You're not relying on the orthogonality in the same way when you make that finite difference stencil. There's the orthogonality is kind of in the stencil, and then you're committing a sin by having a mesh which doesn't respect the orthogonality.
Yeah, this is about a 5-point Laplacian operator.
Yeah.
This is what these conclusions are about.
Exactly. No, which is why I'm making the point that doesn't matter.
It's more general than this. I mean, you can extend that. You can do 9-point Laplacian. You can use any of the formulation. You can try higher order. It's not going to fix it either. So it's not specific to the 5-point Laplacian. It's more general.
No, it's specific to. I mean, that 5-point and similar stencils have assumptions about the orthogonality of the system in the differencing operator. So if you have a differencing operator which doesn't have those orthogonality assumptions in it, such as, for example, the finite element one, then you won't see this.
Or a finite volume scheme with a 9-point stencil should get it better.
No.
Yes.
No.
Can I say something?
Sure.
Sorry. No, okay, so I know exactly about this problem. You absolutely need to take into account the non-orthogonality, and there's a very nice way to do it in a finite volume setting. But there's actually other issues. The example you used, by looking at using the Laplacian of the mapping to compute the curvature normal, I suspect that's a very special problem, and I would like to understand more about that, but that's a very special case in which you will see a second order consistent operator, at least away from areas where you have a discontinuity in your mapping. Okay, so edges and things. But if you were to look at, say, a general function on the sphere, say take just some q evaluated on the sphere, evaluate its Laplacian, compare it to what you might, sort of a known Laplacian, you probably wouldn't even see second order. You would see order 1 errors because of and the reason that the Laplacians typically work to solve Laplace equations is because of superconvergence that you often see in some of these setups, finite volume schemes in particular. And so it might be interesting to try not just that. I mean, it's a nice test case to try kind of, let's look at the Laplacian of the mapping, because we know the solution, it's easy. But I think that's a very special case. Try something a little more.
Yeah, I did. You observed the same problem. It is not that surprising. You can replace the y by a function of y, and you can expect to see exactly the same problem, unless you do very specific ones. For example, the first one we tried were recovering spherical harmonics. And spherical harmonics, if you are not careful, they fall. You can choose a mode which actually doesn't trigger the problem because there is nothing at the pole, or the error is dominated first by larger errors away from the pole. So you do that and you go to whatever resolution, it looks fine. But then if you shift your distribution and you stick the error on the pole, then you see that much earlier. Again, if you solve the inverse problem, it's much more,
right, because of
much more stable.
superconvergence. Yeah, you get this. I don't understand all that stuff. I don't know if Martin's work here, he may understand that a little better.
So, yeah. Finite element may be something too, but people clearly use finite differences or finite volume on the conformal cube sphere. So yeah. I think that's something they should be aware of.
Yeah, no, finite volume.
In this context, finite volume, I think, is just the lowest order finite element scheme, right?
It is the same. Yeah. There's no difference.
There's a whole group of people in France that do these discrete duality finite volume schemes on sort of unstructured meshes.
What I showed here has really nothing to do with, you could see it as working in purely a coordinate space, irrespective of the physical space. So, it's just a property of the mapping that it is very curved. And if you need to estimate curvature terms on the coordinate lines, it's going to blow up. It's very simple. Just something to be aware of if you try to use this grid. But the question is that, an important is, can you fix the grid? Can you fix the grid? There were variants of where I've been proposed of the conformal cube sphere to avoid the convergence problem, which is very much linked to that, of course. So you could think of approaches to do that. I think one approach would be one way you could do it is you could push the singularity closer to the pole so that it would blow up faster, but not have an influence which is fast enough. So your grid would be sort of okay up to some resolution, and then would blow up later on. But that would be okay if you work below this resolution. That would be one way to do it, and that's possible. And another one, which is very important, is you can relax the orthogonality constraint. If you look in practice at the meshes that people use, they are very rarely as orthogonal as this is. If you relax that, then you have a fairly easy way to actually deal with the problem, because you can always you will be able to bound the curvature below, to a threshold which is below the point where your discretization error accumulates. So that could be one way to do that. Yes, you want?
Could you even kind of quantify the amount that you can allow for this relaxation? I mean, you kind of showed that your deviation from the convergence there has a certain factor, right?
Yeah.
And then you can, in a way, you could.
Yeah, there are lots of things you could do. One thing I like about the conformal grid in the context of adaptive methods. For adaptive methods, you have to remember that you need to do all this in real time. Adaptive, you You have to regenerate the metric as you go. If you have something which relies on spring optimization, stuff like that, you don't want to do that. Much too expensive to do that every time step. So you want something which is as analytic as possible and as fast to compute as possible. And the conformal mesh is pretty fast to compute, so you can generate it in adaptively and dynamically. So any method which fixes this should be, to me, would be a big point with that. It scales like that. Hilary, maybe. Yeah.
When you say it's not fixed by a 9-point stencil, do you mean 5 by 5 points in a big cross, or do you mean 3 by 3?
The stuff I've tried is 3 by 3, but I don't think that you can try anything. I don't think that's going to fix it. Just because it's not due, it's just due to what you want is a scheme which could. No, you can't do it because essentially you have two. It's the truncation error of your scheme on the evaluation of the curvature term, and these two sum up, add up. And when the two terms blow up, the errors are going to add up anyway. So you would want a scheme which is symmetric enough with respect to the metric that these errors cancel. I can't see how. It's not obvious to be any classical discrete operator is going to do that.
How do you even do 3 by 3 when it spans the poles? You get 1 point twice, right?
Unstructured stencil. Stencil on unstructured grid.
Even last year then.
So I remember GFDL when they went to the cube sphere. They started with conformal, and they spent a lot of time. They really wanted to make that work. They did the grid relaxation for a while to make it slight, and ultimately they went to equiangular.
Yeah.
And so I think if you have a finite volume or finite element method that can handle an orthogonal grid, you're going to end up on the equiangular.
Yeah, sure. I mean, yes. But to me, that was always, the conformal grid seemed to be reasonably popular and decreased in popularity. So I'm not sure. I never saw the obvious answer was, it's non-uniform. But of course, if you do adaptive, it's much less important because in the end, you can put the resolution where you want.
But I think the MIT group still uses. I think they're the last ones standing, but they still use a conformal.
Yeah, John McGregor still uses it for and
I interpreted John's talk as he's switching to.
He's switching to gnomonic. To me, it wasn't clear. I mean, I don't know. I mean, that could be a very good reason not to. But I think it's more explicit than just saying, there's convergence of the pole and the resolution changes. It's more than the resolution. I think it's more fundamental. But I still think I don't know. Yeah, maybe I will switch to gnomonic.
Well, they have the GFDL group, S.J. Lin and Bill Putnam have a paper on the whole suite of grids, continuous transformation between conformal and mnemonic, and trying to fine tune that parameter.
Okay. Yeah, I think that's it. Thank you.